Okay, now let's look at some special subspaces. The null space of a matrix designated as NUL of A is the set of all solutions to the homogeneous equation AX equal to 0. Okay, so the null space is the set of all X that are in Rn so that AX is equal to 0. Okay, remember that if A is an M by N matrix, that means you've got M rows and N columns. If you were to multiply this by an X, the number of rows in X has to match the number of columns of A. Okay, so A takes a vector in Rn to a vector in Rm. So if X is a solution to AX equal to 0, we know X is in Rn. Okay, so the null space, the null of A is the set of all vectors in Rn so that AX is equal to 0. Now what happens geometrically there is you've got this set of vectors. Okay, so this is Rn. That's our domain. So there's a set of vectors, which is just denoted by this line here, called the null space. Those are all the vectors in Rn, so that when you multiply them by A, you end up getting 0 for the answer. So that means that all of these are being pointing to 0. So if the null space is more than one single vector, then this will not be a one-to-one type of transformation. Okay, so let's look at the system of homogeneous equations. I'm going to let A be the matrix, denoted by the coefficient matrix of 1, -3, -2, -5, 9, and 1. Okay, so that AX is equal to 0 would be the way we would represent this system of equations. Okay, I want to see if U is in the null space of A. Okay, to be in the null space, we know that it has to be an element in Rn, which in this case, A goes from A's a 2 by 3, so A's taking a vector in R3 to a vector in R2. So when you multiply a vector by A, it has to have 3 components, and U does, and you're going to get an answer that has 2 components, something in R2. Okay, so if I want to see if U is in the null space, that means if I take A times U, I should get 0, because the null space is a set of all vectors that when multiplied by A, you get 0. And of course 0 in this case, since it's a vector in R2, would be 0, 0. So A times U, we can easily check to see if it's in the null space by just multiplying. If it's in the null space, we better get the vector 0, 0. Okay, multiplying row by column, we get 5 minus 9 plus 4 is 0. -25 plus 27 minus 2 is 0. Okay, so that is the 0 vector in R2, and so that means U is in the null space of A. They also call it the nullity of A. Okay, so the null space of A is a subspace. Okay? Equivalently, the set of all solutions to a system AX equals 0 of M homogeneous linear equations with n unknowns is a subspace. Because any of these vectors, any of these matrices A, the M by N, can be viewed as equations in a system if it's a homogeneous system. So if I want to see if this really is a subspace, I need to show 3 things are true. So is the null space a subspace of Rn? And I don't just mean subset, I mean subspace. So we have to show 3 things. Well, one more also. First off, is the null space a subset of Rn? And yes, it is. Since A is an M by N matrix, it takes vectors in Rn to vectors in Rm. So this is a subset of Rn. Next thing, is 0 in the null space? to see, remember it's in the null space if it's a subset of Rn, and A times the vector has to be 0. Well, definitely A times 0 is 0. So yes, 0 is in the null space. Okay, the other two things we have to show is if two vectors are in the null space, u and v in the null space, is u plus v in the null space? Well, if u's in the null space, that means A times u is 0. And that means that A times v is 0 if v is in the null space. But we know that A times u plus A times v would have to be 0 as well. And A times u plus A times v is equivalent to A times u plus v, just one of the properties of matrices. And so that means then that u plus v, since it multiplied by A gives you 0, that means u plus v has to be in the null space as well. Okay, so the other thing we have to show, so this is property 1, property 2. The third property to show that it really is a subspace of Rn is to show that if u is in the null space, is C times u in the null space? Well, C times u would, if u is in the null space, that means A times u is 0. Okay? Well, that's equivalent to A times, well, let's just start with this. A times Cu, but we know this is the same thing as just taking the scalar times AU. It's one of the properties of matrices. And so AU we know is 0. And so that means that A times Cu is also 0, which means this vector is also in the null space. So Cu is in the null space of A. Okay, so that proves then that the null space is indeed a subspace of Rn. So that means then that if we take the set of all solutions of a homogeneous equation where you have m equations and n unknowns, that will be a subspace of Rn as well. Okay, so now let's look at H is the set of all vectors in R4 whose coordinates satisfy this. We want to show that H is a subspace of R4. Okay, so if H is the set of all vectors that satisfy this, that means that H has to also satisfy A minus 2B plus 5C minus D equal to 0, and A minus B plus C equal to 0. So the H is the set of all vectors whose coordinates satisfy that, meaning that H is the set of all vectors so that these two equations are satisfied. So they're the solutions to this homogeneous system of equations. So that means that since the set of all solutions to this homogeneous system of equations is equivalent to H, then we know that H has to also be a subspace. Okay? So the solution to this system is a subspace. But the solution to this system is the set of all vectors whose coordinates satisfy this. So that means then that H is a subspace. So H will be a subspace if we can see it as the set of all vectors that satisfy a system of equation. Okay, so now solving an equation AX equals 0 then is equivalent to finding an explicit description of the null space, because we know the vectors that satisfy this is the null space. So let's solve this system and then get a description of all the vectors that satisfy it. That set of vectors will be the null space. So what we're doing is we're just finding an explicit description for the null space. We'll know exactly what it looks like. So I want to find a spanning set for the null space. So to do that, I'm just going to row reduce this matrix. Now, just imagine that you've got a whole column of zeros here for the augmented matrix. And by row reducing, I'm not going to change that last column of zeros. Any multiple of that last column is going to remain 0. So I'm just going to row reduce this matrix and get the explicit description for the null space, which is the solution to the system AX equal to 0. So I'm just going to move row 2 to row 1 just to keep from having to introduce fractions. Okay, now I'm going to get column 1 taken care of here. 3 times row 1 added to row 2. Now negative 2 times row 1 added to row 3. Okay. I'm going to go ahead and clearly we're going to have some free variables here. I'm going to divide this one through by 5. And now you notice if I take negative 1 times row 2 and add it to the last row 3, I'm going to get a row of all zeros. Okay, so we have two basic variables, the x1 and the x3. I have other free variables, so I know that x1 will be equal to 2 times, let's see, let me go ahead and take it one more step to get it in reduced row echelon form, which just means I need to zero this out right here. Okay, so negative 2 times row 2 added to row 1. Okay, so now solve for all the basic variables. So we know that x1 will be equal to twice x2 plus x4 minus 3x5. I want to rewrite it as in a system of equations and then solve for x1, solve for x3. x3 will be minus 2x4 plus 2x5. And we have that x2, x4, and x5 are all free variables. So our general solution then would be 2x2 plus x4, this is x1. x2 is free. x3 would be minus 2x4 plus 2x5, and then x4 and x5 are free. Now if you split this, I'm going to take everything with x2's in one vector, everything with x4's in another, and everything with x5's in another, and then factor out. So I'm going to have x2 times 2, 1, 0, 0, 0, plus x4 times 1, 0, negative 2, 1, 0, plus x5 times negative 3, 0, 2, 0, 1. Okay, so what we just found is we found an explicit description for the solution to this homogeneous equation, which is a solution, the explicit description of the null space. Okay, so the null space is actually going to be the span of the vectors Okay, so that's showing that the null space is that subspace generated by those three vectors. The sum of any multiple of those three vectors will give you the null space. Now, because these are free variables, the three vectors here will be linearly independent. The only way that that sum can be 0 is if all three of the free variables end up being 0. So that, there's the definition of being linearly independent. So this spanning set will be linearly independent. Okay. And notice also that the number of vectors in that spanning set matches the number of free variables.